Hello everybody, welcome to Shaders Monthly. Today we talk about image-based lighting of the Cook Torrance microfacet BRDF. This will allow us to perform image-based lighting for PBR materials. For real-time performance, we follow closely the SIGGRAPH 2013 tutorial by Brian Karras, who works for Epic Games. His tutorial is called Real Shading in Unreal Engine 4, and we are going to use the suggested split-sum approximation. A link to the original tutorial notes can be found in the video description. Before we start, we need a few quick refreshers. Most importantly, the rendering equation, which we have introduced and discussed in detail in episode number 4. The rendering equation calculates the outgoing radiance LO in the direction V for a surface patch at location X with normal N. The outgoing radiance is the sum of two terms. The first term is the emitted radiance LE in the direction V. This term is only larger than 0 if the surface is a light source. The second term is the integral over the complete solid angle of the hemisphere above the surface. The solid angle around the light vector L is denoted by omega and is a variable of integration. Consequently, d omega denotes the differential solid angle. We integrate over the incoming radiance Li from the hemisphere above the surface patch. An incoming radiance Li from direction L multiplied by cosine theta d omega generates an infinitesimal irradiance contribution dE. The infinitesimal irradiance contribution dE is multiplied by the BRDF, which is short for bidirectional reflection distribution function. The BRDF defines how much radiance is emitted by the surface patch in direction V if it receives irradiance from direction L. This way, the BRDF describes the material properties of the surface patch. In episode number 9, we talked about the Cook Torrance microfacet BRDF. It has a diffuse and a specular part. The diffuse part is given by the surface albedo ρd in the range from 0 to 1 divided by pi. The specular part has three terms: Fresnel reflectance, the normal distribution function, and the geometry term. We have chosen a Schlick Fresnel function, the GGX normal distribution function, and a Smith-Schlick GGX geometry term. The last refresher is a slide from episode number 10 about Monte Carlo integration. Using Monte Carlo integration and importance sampling, we can approximate any integral by a sum. Here we have an integral from a to b of f of x dx. This integral is approximated by 1 over capital N, where capital N is the number of samples, times the sum over f of xn, which is the function value at the sampled x location, divided by p of xn. P of x is some arbitrary probability density function called PDF for short. The PDF must fulfill the condition that the integral from a to b of p of x dx is equal to 1. When we approximate the integral by sampling and we sum up the contributions as denoted here, this gives us an unbiased estimator. The theory of importance sampling states that the best PDF, which is the one for which the estimator has the smallest variance, would be p of x equals f of x divided by the integral from a to b f of x dx. This means that the sampling density should be high if the function values are high, and the sampling density should be low if the function values are low. For image-based lighting, the incoming radiance Li is stored in a 2D environment image. This image is mapped on a sphere, a dome or cube that surrounds the scene. We use a spherical environment map here. In any case, the image provides us with the incoming radiance Li from all directions. This means we need to solve this integral from the rendering equation. We have to integrate over the incoming radiance Li from the hemisphere above the surface patch to compute the outgoing radiance Lo. Up here we have the rendering equation. Let's assume the emitted radiance Le is 0. Now we put in the Cook-Torrance microfacet BRDF, which gives us this integral. We can split this sum of the diffuse and the specular part into two integrals. The first integral handles the diffuse part, and we have already discussed the solution in episode number 10. The second integral computes the specular part, and solving this integral is the task for today's episode. Okay, we know now that we want to solve this integral using importance sampling. Because the normal distribution function is dominating the overall shape of our specular lobe and is given as an analytic function, it is a reasonable choice to solve the integral by importance sampling according to the normal distribution function d. This means if the value of the normal distribution function is high, the sampling density should be high, and if the normal distribution function is low, the sampling density should be low. Now there is one problem here. Omega is a solid angle around the light vector L. This is an integral over all incoming light directions L. But the normal distribution function d is a function of the half-wave vector h. This means during importance sampling we have to sample the half-wave vector, not the light direction. Consequently, we need a mathematical expression for the relation between L and h. The half-wave vector h is a unit vector in the middle between the view direction v and the light direction L. Given the light direction L and the view direction v, the half-wave vector h can be easily computed by adding L and v and normalizing the resulting vector to a length of 1. There's a second equation that we need later. Given the half-wave vector h and the view direction v, the light direction L can be computed by a reflection of v with respect to h. To perform the reflection, we project the unit vector v on h with the dot product. The dot product gives us the length of the projection. We take 2 times this length. Then we multiply this value with the unit half-wave vector h and we get this vector. Lastly, we subtract the view direction. This equation computes the light direction L from the half-wave vector h and the view direction v. Here is a visualization of the ggx normal distribution function d ggx of h. As we have discussed in episode number 9, the microfacet model assumes that the orientations of the microfacets follow some distribution around the macroscopic surface normal. We see here that our distribution function depends on the dot product of the surface normal n and the half-wave vector h. The dot product is equal to the cosine of the angle between these two vectors. If we change the view direction, the half-wave vector also changes, and the dot product of the surface normal n and the half-wave vector h changes as well. When the half-wave vector points in the direction of the normal, the dot product is the largest and we get the highest contribution in the view direction. This is because statistically the normals of the microfacets are most likely to point in the direction of the macroscopic surface normal. This yellow lobe here is produced by the value of the normal distribution function for different view directions. If we change the light direction, the half-wave vector also changes. The further the half-wave vector is away from the macroscopic normal direction, the smaller the contribution in the view direction. This is because statistically there are fewer microfacets that are oriented such that they reflect light in the view direction. If the roughness parameter alpha is increased, the orientations of the microfacets are more random and light is collected from a larger range. In this case, the normal distribution function is less dependent on the view direction and its amplitude is smaller. To perform importance sampling of the ggx normal distribution, the PDF in spherical coordinates is chosen to be dggx of h cosine theta sine theta, where theta h is the angle between the surface normal n and the half-wave vector and phi h is the azimuthal angle. The dot product of n and h is equal to cosine theta h, and if we put in the cosine function in dggx, we get this PDF. Let's check if the PDF is already normalized. This means if we integrate the PDF over the whole domain, the result must be 1. For the hemisphere, the range of phi h is from 0 to 2 pi. And theta h goes from 0 to pi over 2. We solve this analytic double integral. And after some calculations, we see, yes, it's normalized to 1 and therefore a valid PDF. Our PDF in spherical coordinates is a joint distribution of the two random variables theta h and phi h. But we see here that in our special case, the joint distribution is only a function of theta h and does not depend on phi h. For independent random variables, the joint distribution is the product of the marginal distributions, which is a basic rule from probability theory. As the joint distribution does not depend on phi h, we sample phi h uniformly. For the hemisphere, phi goes from 0 to 2 pi. Therefore, the marginal distribution of phi is given by 1 over 2 pi, because it is a simple uniform distribution. By solving for p of theta h, we can compute the marginal distribution of theta h. P of theta h equals 2 pi times the joint PDF. This equation for the marginal distribution of theta h allows us to perform inverse transform sampling for theta h. Here is a quick refresher from episode number 10 on inverse transform sampling. Step 1. Compute the cumulative distribution function CDF for short from the probability density function PDF for short. By definition, the CDF capital P of x is computed by the integral of the PDF from -infinity to x. Step 2. Compute the inverse of the CDF. Step 3. Generate uniformly distributed random values u in the interval from 0 to 1. Step 4. Compute random numbers x according to P of x using the inverse of the CDF. Okay, in step 1 we have to compute the CDF. To this end, we compute the integral of our marginal distribution for theta h from -infinity to theta h. However, our distribution is 0 if theta h is smaller than 0, so we can use 0 as the lower limit for the integration instead of -infinity. Once we solve the integral, we get this solution for the CDF. In step 2, we have to compute the inverse of the CDF. We start with the equation u is equal to the CDF from the previous slide. Then we solve this equation for theta h to compute the inverse. After some steps, we get the inverse of the CDF. It is the arc cosine of the square root of some function of u and alpha. U is the value of a uniformly distributed random variable, and alpha controls the roughness of the surface. Okay, with this result, let's visualize the sampling of the ggx normal distribution function. We generate uniformly distributed random values u and v in the interval from 0 to 1. Then we compute the spherical coordinates theta h and phi h of the half-wave vector. For theta h, we use the inverse of the CDF that we have just computed. Our PDF does not depend on phi h, so we sample phi h uniformly in the interval from 0 to 2 pi. Thus, phi h is 2 pi times v. Given theta h and phi h, we can compute the half-wave vector h. Together with the view direction v, we can compute the light direction L with this equation. Let's first choose a very small value for the roughness. When we now start sampling, we see how the half-wave vector does not deviate much from the surface normal. Each green point is the sample position for the half-wave vector. The yellow points are the resulting samples for the light direction. When we compare the sampling positions, we see that the samples for the light direction are distributed over a larger solid angle. If we increase the roughness, the orientations of the microfacets are more random, and the sampled half-wave vector deviates much more from the surface normal. Sometimes the computed light direction is even on the other side of the surface. Obviously, these light directions must not contribute to the irradiance. Now, back to the integral that we want to solve. We still have the problem that this is an integral over all incoming light directions L. But the normal distribution function d, for which we can perform importance sampling now, is a function of the half-wave vector h. We can solve the problem by using a mathematical method from calculus called change of variables or integration by substitution. Using this method, we can change the variable of integration from d omega, which is a solid angle around the light vector L, to d omega h, which is a solid angle around the half-wave vector. To this end, we have to insert this additional derivative d omega h. I have used Leibniz notation here, which denotes the derivatives as the ratio of two differentials. This derivative describes a change in omega caused by a change in omega h. Leibniz notation already vaguely suggests that the change of variable method is a valid operation, because when interpreted as a fraction, both the omega h are cancelling each other out and we have the original integral. However, when performing a change of variables, we usually have to change the limits as well. But we are already integrating over the complete hemisphere, and we know that there can be no contribution from the backside of the surface. So this is already the maximal range. Therefore, in our special case, the limits of integration stay the same. As introduced in episode number 4, the solid angle can be parameterized in spherical coordinates theta and phi. For a unit sphere, d omega is equal to the area of this patch, which is d theta in the polar direction times a d phi step in the azimuthal direction. But the size of a d phi step depends on theta. When theta is equal to 0, the contribution is 0, and when theta is equal to 90 degrees, the contribution is a full d phi step. Therefore, we have to use the factor sine of theta to scale the d phi step. Overall, d omega is sine theta d phi multiplied by d theta. We use this result to replace d omega here, and we can use the same equation for d omega h. The problem is now shifted to finding a relation between the spherical coordinates of the light direction and the half-wave vector in the coordinate system of the surface normal. But the normal distribution function d, for which we can perform importance sampling now, is a function of the half-wave vector h. In this visualization on the left side, we look at the plane spanned by the surface normal and the view direction. We are interested in a relation between the polar angles theta h and theta. In the coordinate system of the surface normal n, this relation is not trivial. However, in a spherical coordinate system in which the view direction is the z-axis, the relation of the polar angles is quite simple. The angle between the view direction and the half-wave vector is half of the angle between the view and the light direction. In fact, this is why it is called half-wave vector, and we have defined the half-wave vector this way. Because of this simple relation, the computation of the derivative d omega with respect to d omega h is performed in the special spherical coordinate system in which the view direction is the z-axis. The star superscript indicates that we are referring to these special spherical coordinates. The relation is simple. Theta star equals 2 theta h star and phi star equals phi h star. We insert this result and get sine 2 theta h star 2 d theta h star d phi h star over sine theta h star d theta h star d phi h star. These terms cancel each other out. Sine 2 theta h star is equal to 2 sine theta h star times cosine theta h star. These two sine theta h star terms cancel each other out, and we get a factor of 4 cosine theta h star. Cosine theta is the same as n dot L, so these terms also cancel each other out. These two 4's as well. Theta h star is the angle between the view direction and the half-wave vector. Thus, we can replace cosine theta h star with a dot product of v and h. Perfect, now we have an integral over d omega h which is the solid angle around the half-wave vector. We can transform it into a double integral of the two variables theta h and phi h. Note that here we use theta h and phi h without the star, which means these are spherical coordinates relative to the surface normal. Now, let's solve this double integral by importance sampling. This is our function f of theta h and phi h. We use our chosen PDF, d of h cosine theta h sine theta h. Again, some terms cancel each other out. In the denominator we have n dot v and cosine theta h, which is equal to n dot h. And on top we have f times g times v dot h times li of l. Finally, after solving all these problems and integrals, this is our overall result for importance sampling of the specular part of the Cook-Torrance microfacet BRDF. We generate uniformly distributed variables u and v. For each sample we compute theta h and phi h. We compute the half-wave vector h in Cartesian coordinates from its spherical coordinates. With h and a given view direction v, we compute the light direction l. Overall, we take capital N samples and compute this sum. This is a bias-free solution that we could implement. This means for large values of capital N, we converge towards the correct solution. Therefore, this solution can serve as a ground truth. But the result depends not only on the surface normal n, but also on the view direction v. Consequently, we cannot pre-compute this sum and store it in a 2D pre-filtered environment map that we can use for real-time processing. For real-time processing, Brian Karras suggests a split sum approximation in his tutorial. The split sum approximation deliberately introduces an error that produces biased results for the sake of real-time performance. This means, in contrast to the equation on the previous slide, this solution has a systematic error that doesn't go away when we increase the number of samples. In this approach, we split the sum into two parts, which are stored in two pre-computed textures. Here is the original sum. We split it into a sum over the incoming radians, which we call pre-filtered environment map and denoted with T1, and a sum over all the other terms, which we call BRDF integration map and denoted with T2. Again, this is mathematically not correct, it is just an approximation. The importance sampling of the half-wave vector for both parts, T1 and T2, stays the same as before. When we compute T1, the viewing direction is not known at the time of the pre-computation. Therefore, a perpendicular viewing direction is assumed, which means the view direction v is set to the direction of the surface normal n. This is the next systematic error that is introduced. Because we chose a perpendicular viewing direction here, this error is the largest for grazing viewing angles. The results for different values of the roughness alpha can be stored in the mipmap levels of the texture. Alpha is equal to rp squared, where rp is Disney's user-friendly perceived roughness value in the interval from 0 to 1. One possible mapping between rp and the mipmap level is that we take the current mipmap level and divide it by the total number of mipmap levels that we are using. Here you see the results for the mipmap levels of a pre-filtered environment map. Mipmap level 0 has the highest resolution and the perceived roughness rp is 0. For the largest mipmap level, which is level 5 in this example, rp is 1. For a higher roughness value, the distribution of samples is wider, and thus high frequencies in the input image are averaged out. Those low frequency results that we get for larger roughness values can be stored in a mipmap level with a lower resolution without losing much information. The second texture that we have to pre-compute is the BRDF integration map. We use a Schlick approximation for the Fresnel term f, which is given by this equation. The idea here is that our pre-computed values should not depend on f0. Therefore, we rewrite the equation to get a sum of two parts. The first part has f0 as a linear factor, and the second part does not depend on f0. Now, when we put this result for the Fresnel term into our sum for T2, we can split the sum into two parts. This is the first part. Because f0 is a linear factor, we can move it in front of the sum. This is the second part, which does not depend on f0. Both parts can be pre-computed, and each part could be stored in a grayscale texture, which is parameterized in the x direction by n.v and in the y direction by the roughness Rp, both in the range from 0 to 1. This is the result for part 1 of the BRDF integration map. This is the result for part 2. Finally, both grayscale textures can be combined in the red and green channels of an RGB texture. Overall, we need to pre-compute 3 textures. First, the diffuse pre-filtered environment map from episode number 10. We use the env map value that is stored at the location to which the surface normal is pointing. Second, the specular pre-filtered environment map. The results for different roughness values are stored in the mipmap levels. We use the env map value that is stored at the location of the reflected view direction, denoted by RV here. Third, we have the BRDF integration map that is parameterized in the x direction by n.v and in the y direction by the roughness Rp. To implement the required shaders, we use the GSN Composer at gsn-lib.org as a shader editor. The GSN Composer is a web-based tool that I created especially for teaching shader programming. But you can use any other shader editor as well. We are writing pure OpenGL GLSL code which you can use everywhere. Links to examples that execute the same shader code using C++ or Java can be found in the video description. The implementation is based on our example from episode number 10, in which we performed image-based lighting for the diffuse part of the BRDF. Click Project and type in the project name, Shaders Monthly 10, and click Open Existing. We clone this complete project to a new project. Press the Clone Project button. Type in the new name. For me, this is Shaders Monthly 11, and press the Clone Project button. Then open the graph Pre-filtered Diffuse and press Play in the Time Control panel. This graph loads an environment image and computes the diffuse pre-filtered environment map with this shader node. We need to change the shader such that it now computes the specular pre-filtered environment map. We set the number of samples to 512 and the width to 1024 and the height to 512, which are the dimensions of the input environment map. Let's have a look at the shader code. We select the shader node and click the Edit Code button. This dialog is the shader editor of the GSN Composer. In the top section we can define the vertex shader, and in the bottom section the fragment shader. Pre-filter env-map specular. The first change that we need to make to the shader is to modify the inverse transform sampling for theta. This is the old equation to sample the light direction for the diffuse part. We replace it with a new equation to sample the half-wave vector for the specular part. Float theta equals arc cosine square root of 1 minus u divided by 1 plus alpha times alpha minus 1 times u, where u is a uniformly distributed random variable which we get from the random PCG3D function in this line. Float u equals random.y. Float alpha equals roughness times roughness, where roughness is Disney's user-friendly perceived roughness value in the interval from 0 to 1. We set this value with a uniform variable, uniform float roughness. Description roughness. Default val equals 2.0. Apply code, recompute. Okay, this looks promising. But wait, we are sampling the half-wave vector and not the light direction. This is the half-wave vector in the global coordinate system. Vec3h. Next, we compute the light direction from the view and the half-wave vector. The view vector is assumed to be in the direction of the normal, so Vec3v equals normal. The light direction L can be computed by a reflection of v with respect to h. Vec3L equals 2.0 times dot vh times h minus v. Or we can use the built-in GLSL reflect function. Now let's make sure that the sampled light direction is not on the backside of the surface. We have seen in the slides that this might happen if the roughness value is large. We compute the dot product of the normal and the light direction. If the dot product is negative, the light direction is on the backside of the surface. N dot L equals dot normal L. If N dot L larger than 0.0, direction to spherical env map of L. Apply code, recompute. Okay, this looks different. So again, this is the result when we use H, and this is the correct result when we use L. In his tutorial notes, Brian Karras suggests weighing each sample by N.L. This is different from the formula in the slides. I assume he found this additional weighting factor by comparing the results of the split sum approximation to the ground truth. Times N.L here. Flow total weight equals 0.0. Total weight plus equal N.L divided by total weight. Apply code, recompute. Okay, the difference seems to be rather small, at least for the currently selected roughness value. Apply code and close. For a roughness value of 0.0, we get a copy of the input. This is the result for a roughness value of 0.2, 0.4, 0.6, 0.8, 1. For a higher roughness value, the output becomes more blurry. High frequencies are removed, but we also see more noise. Let's connect this other, more difficult environment map. 0.0, 0.2, 0.4, 0.6, 0.8, 1. The sampling noise is very strong. We can increase the number of samples to 1024, which does not help much here. Instead, we can low-pass filter the input by using a higher mid-map level. 1, 2, 3, 4, 5. Now we save the specular pre-filtered environment map for different roughness values. For a roughness value of 0, we save the output to Teatro Massimo 1K pre-filtered specular level 0. For the next level, we set the roughness to 0.2 and reduce the resolution by 2. This means 512 times 256. Increase the mid-map level to 2. Maybe also increase the number of samples a bit, 4096. This looks okay. We save it as Teatro Massimo 1K pre-filtered specular level 1. Now again for a roughness of 0.4, which we save to Teatro Massimo 1K pre-filtered specular 2. Roughness 0.6 to level 3. Roughness 0.8 to level 4. And roughness 1 to Teatro Massimo 1K pre-filtered specular level 5. Next, we need to generate the BRDF integration map. We clone most of the nodes from here. We open the shader code. We replace prefilter envmap specular with vec2 integrate BRDF float roughness float n.v. We add an attribution for the split sum approximation idea, adapted from real shading in Unreal Engine 4, Brian Karras Epic Games. First, we need to compute the view direction. View direction in normal space from spherical coordinates. Vec3v equals vec3 sine theta view times cosine phi view, sine theta view times sine phi view, cosine theta view. We can compute theta from n.v. Float theta view equals arc cosine n.v. The value for phi view can be freely selected. If we set phi view to 0, we get simpler equations for v. The cosine of 0 is 1. The sine of 0 is 0. With phi view equals 0. We don't need these lines. Vec2 result equals vec2 0.0. The sampling of the halfway vector can stay the same. We need h in the local coordinate system of the normal, so this is our h. We need a few dot products. Let's start with float n.l. Because the normal is pointing in the z direction in the normal space, which means it is equal to 0, 0, 1, it follows that n.l is equal to the z element of L. We clamp it to the range 0 to 1 because we know that the sampled light direction might be on the backside of the surface. Same for n.h. Float n.h equals clamp h.z 0.0, 1.0. Float v.h equals clamp.vh 0.0, 1.0. If n.l is larger than 0.0, we can now simply implement the equations from the slides. Float g equals g smith, n.v, n.l roughness. Float g vis equals g times v.h divided by n.h, n.v, which is this term. Float fc equals pow 1.0 minus v.h 5.0, which is this term. Result.x plus equal 1.0 minus fc times gvis. Result.y plus equal fc times gvis. Divided by float n. We need to copy the gsmith function from episode number 9. Here we use interpolated text coord.x, interpolated text coord.y to compute the current pixel location. Finally, let's call our new function. vec2r equals integrate BRDF interpolated text coord.y interpolated text coord.x outcolor equals vec4 r 0.0, 1.0. We can remove unused functions. We don't need this. We don't need this. This also. And remove unused uniform variables. Apply code and close. Let's use a width and height of 256. We save this image to BRDF integration map. Done. We have pre-computed everything that we need. Okay, now perform the image-based lighting. We open the graph IBL diffuse. We make some space here. Here we load all the required textures. We insert the integration map. To load our pre-filtered specular levels, we use the node public parameters, compute, filename, getAll. Here we can filter the input to contain specular level. We get a vector of 6 file names, which we can pass to a load node. When we vectorize the output, we get a vector of 6 images. We then pass this vector to a node of the type 3D, compute, mipmap, mipmap. Uniform sampler 2D BRDF integration map, minFilter equals linear, macFilter equals linear, and uniform sampler 2D envmap specular, minFilter equals linear, mipmap linear, macFilter equals linear. We also need uniform int mip level count, description equals number of usable mipmap levels in envmap specular, default val equals 5. We add a new function. Adapted from real shading in Unreal Engine 4, Brian Karris, Epic Games. Vec3 specular IBL, Vec3 F0, float roughness, Vec3n, Vec3v. Float n.v equals clamp.nv 0.0 1.0. We compute the reflected view direction. Vec3 r equals reflect minus vn. We compute the texture coordinates of the reflected view direction in the specular envmap. Vec2 uv equals direction to spherical envmap r. We get the value from the specular envmap using the texture LOD function. The mipmap level is computed from the roughness and the mipmap level count uniform variable. Vec3 t1 equals texture LOD envmap specular uv roughness times float mipmap level count .rgb. We get the value of the BRDF integration map. Vec4 BRDF integration equals texture BRDF integration map Vec2 n.v roughness. Vec3 t2 equals f0 times BRDF integration.x plus BRDF integration.y. We multiply the two terms to perform the split sum approximation. Return t1 times t2. Now we scroll down to the code that performs the image-based lighting for the diffuse part. For metals, the diffuse part must be 0. So we put Vec3 rho d equals 1.0 minus metallic times base color, and replace base color with rho d here. Some implementations that aim for real-time performance do not use any Fresnel term for the diffuse part. However, as a coarse approximation to achieve very basic energy conservation, 1 minus the f0 value can be used for image-based lighting. In the literature, there are more advanced models for the combination of diffuse and specular reflection, but we just implement this simple approach here. As we know from episode number 9, the dielectric f0 is computed from the reflectance parameter by Vec3 f0 equals Vec3 0.16 times reflectance. In the case of metals, the base color value contains the f0 value. f0 equals mix f0 base cal metallic. Rho d times equal Vec3 1.0 minus f0. These are the changes to the diffuse part. Now we use our new function for the specular part. Image-based lighting, specular part, radiance plus equal, specular IBL, f0 roughness, n view dir. Apply code and close. We need to connect the two textures. Let's see what we have. Nice, this looks pretty good. Maybe increase the reflectance value. This is 1.0. Okay, too much, maybe 0.5 is reasonable for this model. Let's turn the specular part off to see the difference. Off, on, off, on. We can also override the roughness value that we read from the texture. This way we get the same roughness for the complete mesh. This is roughness 0.0. This is roughness 0.2. This is 0.4. We can also set the metallic value to 1.0. Okay, that's it for today. If you have questions, use the comments or get in contact with me. As always, if you prefer C++ or Java source code, this can be found in the video description. But the story doesn't end here. For example, we can further reduce the noise in our pre-filtered environment maps by using a low discrepancy sequence instead of random samples. But this is a topic for the next episode of Shaders Monthly.